Hello everyone. In this set of upcoming lectures, we will be discussing about the auto-regressive models. Now that we have come to the end of discussing diffusion models, next set of generative models that we are going to discuss are what are known as the auto-regressive models. Auto-regressive models. Now, these auto-regressive models are historically well known to be used in multiple tasks such as time series analysis and sequential data, handling sequential data, and so on. Examples of these auto-regressive models historically have been the classical linear prediction or AR models or ARMA, auto-regressive and moving average models, and so on. Some of the recent examples of auto-regressive models are models such as recurrent neural networks and pixel CNN and so on. Now, the most recent and widely used auto-regressive models are what are today known as GPT, generative pre-trained transformers, which form the basis for all the generative models that you see these days, sequential language model based generative models that we see these days. This include GPTs and commercially available models such as GPTs and Gemini and Claude and these kinds of models. They are all auto-regressive in nature. So let us look at the definition of what an auto-regressive model is, and we will look at one specific class of auto-regressive models, which are the transformer-based language models. As an example of auto-regressive model in this course, because as we move on, we will look at different ways of training these auto-regressive models, fine-tuning them and also aligning them with a particular type of human required output and so on. So it is important that we look at the construction of this particular class of auto-regressive model, which is called the transformer-based language model. Okay, so let's start with the definition of auto-regressive model. So most of these auto-regressive models are built on data that is sequential in nature. Sequential in nature. So what does it mean to say that data is sequential? So let's say that I can express my data point x as a set of intervals. Let me call it as x1, x2, x3 up to x capital T. Now this is one single data point. So this is a please note the change in notation. We have been using x1 to xt to denote T different latent variables in the context of a diffusion model. Here in the auto-regressive model context, we look at x1 through xt as the sequences of sequences that define one single data point. So an example for a sequential data point can be natural language sentence. This very sentence that I wrote, which is a natural language sentence, is an example for a sequential data point where every word here can be represented as one constituent element of this sequential data point. The other example can be, let's say, a multivariate time series. Multivariate time series, and one can even look at an image as a sequential data by scanning every pixel, arranging every pixel in a sequential way. So you can go from left to right, top to bottom, and arrange all of the pixels one after the other, and one can look at an image also as a sequential data point. Okay, so now in all our upcoming discussions, we will assume that we will work with a single data point as we are doing with the other models. So everything that we do with a single data point can be extended to one data set of multiple data points drawn from a distribution just by having an outer expectation with respect to the distribution of interest. Okay. The problem still remains the same, that given multiple samples drawn from an unknown distribution, so this is drawn from an unknown px. So this is drawn from an unknown px as usual, and we want to learn to sample from this particular px. So that is the problem that we have been solving throughout the course. Okay, the goal is estimate px. It still remains the same, just reiterating for the sake of completeness. Estimate px and learn to sample from it. So this is the one problem that we have been solving from the beginning of the course, right? So given data points that are sampled ID from an unknown distribution, we just want to estimate the distribution and learn to sample from it, and we looked at multiple ways of doing this. Now for the data that has this particular type of topology, which is a sequential nature, the kind of underlying model that is used to model px is little different, and one of the families of models is called the auto-regressive model. So recall that we have used multiple formulations for p theta. One was represented using a neural network, and we use the fact that we can use samples from an arbitrary distribution and a neural network to transform that, and we used variational divergence minimization to find the parameters, that was GANs. In VIEs and diffusion models, what did we do? We expressed the model distribution using a latent variable model, and we used a lower bound on the likelihood function and optimized it using neural networks. In auto-regressive model though, so p theta in AR models, so let me write that. The solution still remains the same. The solution for the above problem still remains the same. Parameterize px and learn the parameters. Parameterize px using a model p theta and learn p theta. Of p theta by optimizing, or rather minimizing, a divergence metric. So the story still remains the same, that we are trying to learn the parameters of the model p theta by optimizing for the parameters by minimizing a particular divergence metric. By optimizing divergence metric. This philosophy still remains the same. So mathematically speaking, we find out the theta star that would minimize some divergence metric, which can be KL divergence, between px and p theta. So we also saw that this was equivalent to maximizing the log of the likelihood p theta of x, so expected log likelihood. This was equivalent to maximizing the expected log likelihood, where the expectation is with respect to px, right? This also we saw, and this is what we called as the maximum likelihood estimation. And we even with auto-regressive models, the exact same problem is solved. Okay, so just that the kind of parameterization that we use for p theta is very different. Okay, so this is the problem that we are going to solve. So in auto-regressive models, p theta will take this particular form. So p theta of x, the likelihood of a particular point p theta of x, which is equal to p theta of x1, x2, x3, so on up to xt, because every single data point now is a sequence of t number of tokens, if you may call it that, is given by chain rule of probability, which would simply say that you just take the product of all of these probabilities from so p theta of x t given x, all the x that precedes this, where x then t, this symbol is simply the set of all tokens starting from x1 to x t minus 1. This is the classical chain rule of probability. We are simply saying that this is the definition of an autoregressive model, where the likelihood of a particular data point, which is a sequence, is modeled as the product of multiple conditional distributions of each of the single data point xt conditioned on everything that precedes that. Okay, so see, one can look at sequential data as a random process as well. So what we are actually doing is modeling the likelihood of the entire sequence of a random process as product of multiple marginals, where every marginal is xt, the likelihood of a particular point xt, given that we have observed everything before that xt. So this is the definition of autoregressive model. The reason this is called autoregressive is that every xt now, right, is made a function of all the x that precedes it. So it is sort of regressing on self. This is one data point, and xt is now given as something that depends on all the data points that precedes it. So it is regressing on self. Okay, the history, that's why the name autoregressive, it is regressing on self. So all the models that we just discussed about, right, including GPTs and AR models and RNNs, belong to this particular family. So how are they different from each other is the way they define the underlying p theta. Okay, so let us look at few examples for autoregressive models. So examples of autoregressive models. The first example that we will look at is for what is known as the AR model, which is a classical AR model. So these techniques date back to several decades prior to the current times. So these ideas were there. The only thing is after the advent of neural networks, we have better function approximators and we can look at multi-parameter models, but the idea of autoregressive models existed for a long time. So here in the classical AR models, a given data point xt, okay, is modeled as a linear combination of p previous data points, so ai times x t minus I plus some epsilon I. So where epsilon I is, so all these AIs are learnable parameters. These are learnable model parameters, and there are p of them. These are learnable model parameters, and epsilon I is simply noise that is added to every data point, which is Gaussian. Okay, it's a fixed Gaussian noise. So this is also called the pth order linear prediction. So p is a hyperparameter here. How many previous data points that you choose to regress over is a hyperparameter, and this is simply a p parameter model because all that we need to learn are p number of coefficients. This is the classical autoregressive or linear prediction modeling. Here we assume that data comes from a Gaussian distribution because, as you can see, every data point is assumed to be a linear combination of previous data points plus some noisy perturbation. One can very easily see that the xt here behaves like a Gaussian because it is simply an affine transformation over a Gaussian random variable. So this is the Gaussianity assumption that is made. Okay. Now these models are even though they are pretty good in modeling data, that does not have too much complexity or dependency between the previous points, but they cannot model very complex sequences such as natural language. Okay, so people move to what are called as the neural autoregressive models. So neural AR models where p theta of x t given x less than t, this is modeled as some neural network which is a function of all the x's that is less than t. So this is the family of neural AR models, and this is trained usually with maximize the ML estimate, the ML objective, maximum likelihood objective, using backpropagation algorithm. So these neural networks can be anything. So these can be, let's say, a fully connected multi-layer perceptron, or this can be a CNN, or this can be a recurrent neural network, and so on. So this was another class of models that are autoregressive in nature. So you have a neural network that would take all the data points before a particular given time index t, and it predicts what p of xt is by maximizing the likelihood. These are these were also called neural language models when they were proposed. So after that, there were a little bit of more complexity that was added to these neural AR models by using these architectures called recurrent neural networks, which are also one family of autoregressive models, recurrent neural networks. Abbreviated as RNNs. So all the family of models that you see, such as GRUs, gated recurrent units, and LSTMs, long short-term memory networks, and so on, belong to this family of recurrent neural networks, where the idea is that there is a hidden state that is assumed. So the way a recurrent neural network works is, so you make HT as a hidden state to be equal to some function f theta of the previous hidden state h t minus 1 and x t minus 1. This is parameterized by theta, and the next data point xt is predicted as some other function g phi of ht, the th state, and sometimes xt minus 1. So this is the general form where f theta and g phi are learnable nonlinear functions. These are learnable nonlinear functions. Depending upon the form of f theta and g phi, there are several family of recurrent neural networks. You change f theta and g phi, you get different family of recurrent neural networks, such as GRUs and LSTMs and so on. So now in this course, the objective is not to go to architectures as we have seen so far. The objective is to look at the formulations of how the broader class of models are working. So I will not go to the details of architectures. Interested readers can go and look at architectures per se. So these were recurrent neural networks. The idea was to do what is called as the parameter sharing across time. Across time or the sequences. The idea here is that the parameters theta and phi are kept the constant across different time steps of the sequences. So what happens is that ht, so let's say h1 will be equal to f theta of h0 and x0, and we have x1 to be equal to g phi of h1, and if you write h2 is equal to f theta of h1 comma x1, and we have x2 to be equal to g phi of h2 and g phi of h2 and so on. So now across time, no matter what time steps we are looking at, the theta and phi remains the constant. So this is called parameter sharing across time. Okay, so this is how RNNs, recurrent neural networks, could handle sequences of different length. So there is, since we are sharing parameters across time, there is no constraint on how long the sequences should be. So a sequence can be of any length. Okay, while this gives RNNs this advantage that one can make sequences arbitrarily large, this also leads to another famous, or rather infamous, problem called the vanishing gradients problem. So the issue of vanishing gradients, where the gradients will have very low magnitude with increased sequence length, with higher sequence length. We'll not go into details because, as I said, this is only an overview of how the literature progressed. What happens is, since the parameters are shared across time, suppose you have a very long sequence, while training these sort of architectures using gradient descent, so what happens is that the same parameters have to be multiplied multiple times in the while computing the gradients, and that would lead to the magnitudes of the gradients getting smaller and smaller as we move more and more to the left of the sequences while we are traveling through the RNN networks architectures. And why is this important? This is important because suppose you want to model sequences of larger lengths, then the model would not facilitate it because the gradients would vanish if you have the sequence lengths to be very large. The other way to look at this is that to generate the tth sequence, we need to depend on the tth hidden state or tth representation, and this tth representation is the only vector that is burdened with the task of encompassing all the information that is there from x0 till xt. Right? The dependence on xt over x0 is via this ht, which is the intermediate representation or the tth hidden state, and this tth hidden state is tasked with this task of compressing all the information regarding all the previous data points starting from x0 till xt minus 1. Okay, so that is, this means that if we look at sequences of larger length, then this ht may not be capable of compressing all that information that is required to generate the data point xt. Okay, so these were the problems, the known problems that were there with the RNN kind of autoregressive architectures. To come up with this, people came up with this idea of attention mechanism or attention based models.